So hi, thank you for the introduction, Unit. I hope I'll do as good job as you did in the beginning of presenting this paper. So I'm going to talk about zero-knowledge proof of proximity. And our starting point, good. So our starting point is property testing, produced by Ronit here and Sudan and Goldrush, Goldwasser, and Ron and 98. And our setting is that we have huge inputs, which throughout this talk I will denote by n. And because they are huge inputs, we don't want to read them all. We don't want to run in time n. So we're going to talk about sublinear time. And specifically, our algorithms will not be able to read the entire input. So to mitigate the fact that they can't read the entire input, what we actually require is some promise problem. So our algorithm should decide whether some string has some property pi, or it's far from having this property. And far usually means in Hamming distance. So yesterday we saw an example of a property tester for the language, for the property of palindrome, which simply choose a random index in the first half of the string and check that it's equal to the corresponding index in the second half. We also saw yesterday that not all properties have very good testers. Specifically, we saw the property of double palindrome, which is a string that is a concatenation of two palindromes. For example, this one. So the first part of the string is a palindrome, and the second part of the string is also a palindrome. And we saw that there is a property tester lower bound for this property. Namely, every property tester that manages to distinguish between, to solve this promise problem has to make a lot of queries and square it, at least square root n number of queries. And it is better than reading the entire input, but still, if the input is huge, it's very high. So also yesterday, we saw a different model where we allow the tester, in which case we refer to it as a verifier, to interact with a prover and maybe help the tester solve this problem. So we also actually saw that the double palindrome has a very efficient proof in this setting, which we call proof of proximity. And the proof is very easy. So here's the string, and the prover just says, okay, here. Look here. Now you can check that, now you can run the tester, the palindrome tester, and check that this side is a palindrome and that this side is palindrome. So this is great. We have a very efficient verifier now to test if this is in double palindrome. But I want to point out that this proof has one big disadvantage. And the fact that it reveals a lot of information about the input. Specifically, it reveals that not only that the line exists, but actually where it is. And even more, now our verifier, our very slow verifier that couldn't decide by himself if this is double palindrome or not, can now go and prove to other very weak verifiers that this is actually a double palindrome. So this proof actually reveals a lot of information, which leads us to the question we're dealing with, is what can we prove in zero knowledge to a sublinear time verifier? And the too long didn't read answer is some interesting properties, but not all. So this is the takeaway. Good. So let's first remember or define what is proof of proximity, and specifically want the interactive version of the proof of proximity. So we have some input x, but it's in the sky, and it's in some property pi. And we have an unbounded prover that has access to the entire input. So you can read the entire input. It's very strong, but we want the prover to prove to the verifier that x actually has the property pi, but this verifier is much weaker than the prover. And specifically, it has access only to much fewer bits of the input than the prover. So now the prover and the verifier can interact, and the verifier should accept with high probability. So this is the completeness requirement for interactive proof of proximity, which I will call IPP. For the soundness property, what we have is this x is now epsilon far from having the property pi. Now pi is very far cloud from this x. And also we have a malicious prover who tries to convince the verifier that this actually has this property. But it doesn't succeed. This is the soundness requirement, and our verifier should reject with high probability. So in the end, combining the completeness and the soundness, what if the verifier accepts, he knows that x is close to being to having the property pi, hence the name proximity in this board. So given this model, now we want to add zero knowledge to it. And to doing so, let's first remind ourselves what is the original motivation from zero knowledge, from the original paper by Goldwasser, Micali, and Rakov that introduced zero knowledge. So the original intuition behind the definition of zero knowledge was that what the verifier sees should be something that the verifier could have computed for himself. So this intuition led to the simulation-based definition that we'll see next. But first I want to say, so the same intuition can carry out to our setting, only that the computation here we talk, that the computation we care about are all sublinear time. And in fact, there is a very big conceptual difference than the original definition of zero knowledge. In the original definition, or the classical definition of zero knowledge, what we actually wanted to hide was an NP witness. So think, for example, of graph free colorability, where a prover wants to convince a verifier that the graph is free colorable, but he wants to do it without revealing the actual coloring of the graph. So here, what we actually wanted to do is to hide the NP witness. In our case, what we actually want to hide is the input. So the verifier is sublinear time verifier. It cannot read the entire input. And we don't want from following the proof that he will be able to learn something that he couldn't have learned by himself. So this is the main intuition behind our definition and what we want to gain in this setting. Okay, so let's see how we define it. So zero knowledge IPPs, or short we say ZKPP. So this is our completeness case. We have the verifier, a sublinear time verifier, talks with the prover. Prover has full access to the input X, and the verifier has very limited access to the input X. So in zero knowledge, we don't have the prover anymore because we want to simulate it by ourselves. We want the verifier to be able to convince ourselves. So actually, these parts do not exist for the verifier. So we also sometimes want to consider zero knowledge for malicious verifiers, namely verifiers that try to exploit the prover and telling him and making him reveal more information than what he actually wants to do. So we say that the protocol is zero knowledge if this interaction, the same interaction, now that I didn't change the errors, or the same errors, can be simulated by the verifier. Namely, we think of it as the malicious verifier interacts with a simulator, but this simulator is in the same complexity of the verifier. So is it the same size of the verifier here? And also have access to roughly the same amount of bits from the input that the verifier has. So if this simulator manages to simulate the interaction between this verifier and the prover, then we say that this proof is zero knowledge, while accessing only limited amount of the input. Good. So that was the model, and before moving on to our result, I want to point out that there are two recently introduced models that are related to ZKPP. The first is zero knowledge PCPs of proximity by Shine and Weiss, and the second is zero knowledge interactive oracles by Benselson et al. But due to time constraint, I will not talk about the differences between our models. I'm happy to talk about it more offline. Good. So here are main results of the paper. So the first one, as Ronit mentioned, that we show that zero-knowledge proofs can be much better than property testing. Specifically, we show that the property of a permutation has a very efficient zero-knowledge proof of proximity, where the verifier runs in polylogarithmic time in the input. But permutation, actually, it's not very difficult to see that it doesn't have a property tester that runs with less than square root n the length. Our second result is a lower bound. So this is some interesting properties that we can do, but not all. So our second result is a lower bound to show a property that has a very efficient IPP, but every zero-knowledge proof of proximity for that property, even if it's honest verifier, namely that the simulator has to simulate only the honest interaction, must be some polynomial in the input level, some fixed polynomial. So this is a very strong separation between IPP and even honest verifier zero knowledge. So in the rest of my time, I want to give you a taste about the protocol for permutation. So what is a property of a permutation? So a property in a permutation is given to us by a truth table of numbers from 1 to n, or this is the claim, 1 to n. They are indexed from 1 to n. And what we want to ask ourselves is f is a permutation or epsilon far from being any permutation. And I want to point out that this actually, the zero knowledge, or at least the honest verifier version of this zero knowledge proof of proximity actually has an application that was noticed very early in crypto in the non-interactive zero knowledge protocols for NP based on trapdoor permutations. We will review the Belar-Young solution to this. Okay, so let's see interactive proof of proximity for permutation. So we have the verifier, we have the prover, and the verifier chooses a random y. So this y will be in the image of f, send it to the prover, and the prover finds a pre-image of y and send it back to the verifier. The verifier now checks that f of x is equal to y. Very simple proof. So completeness is easy. It's very direct. Soundness, I will omit. I just want to point out that if f, and we will see it after, if f is far from being a permutation, then it actually has to shrink a lot. The size of the image is small, so the probability that this y has a pre-image is not very high. This is where soundness comes from. But what I want to focus on this protocol is its zero-knowledge properties. Also note that the verifier is very efficient. It makes only one query to the input. So this protocol actually is an honest verifier, zero knowledge. So let's see what happens in the interaction. So in the interaction, there is a random image and its pre-image. So this is a random pair of image and its pre-image computed backwards. First you compute the image and then the pre-image. To simulate it, we can do something very easy. So we can, instead of going backwards, we can go forward. We will choose a random x from 1 to the n and just compute the function on this x and output y and this x. So this is a perfect simulation for this protocol. But this is only for the honest verifier that actually chooses y at random. What about the malicious verifier? So what does malicious verifier do? We don't really know. It chooses some y prime. Let's say it chooses y prime to be 17. Send it to the prover. The prover finds such x such y prime is 17 and send it to the verifier. Now the verifier learned what is the pre-image of 17, which is very bad for us. And we want to prevent it. We want to protect 17 for some reason. So this is actually not a malicious verifier zero knowledge protocol. And so what was the problem here? Our problem is how to choose y. So the prover cannot be sure that the verifier chose y at random, but the verifier cannot just let the prover choose it because this will hurt the soundness property. So somehow we need to choose y such that both the prover and the verifier know that this is uniform. More concretely, what we want is a protocol to choose a bit b such that the following holds. If f is a permutation, then the prover knows that b is uniform. If f is far from a permutation, then the verifier knows that b is uniform. So this is our goal, and we show how to do it. And we'll finish with that. But at this point, you should scream and say, wait, Simpson did it. Well, not Simpson did it. Goldwasser, Vadan did it in the general transformation of honest verifier statistical zero knowledge to general statistical zero knowledge. But we give a simple solution in the setting of this permutation. So here is our protocol, our bit sampling protocol. So we want to sample a uniform bit. So the verifier, instead of choosing y, it also chooses x, so the pre-image of y, and it chooses some pairwise independent hash function. And it sends y and h to the prover, but keeps x as a secret for himself. The prover, after seeing y and h, chooses a random bit and sends that to the verifier. Now the verifier reveals x to the prover, who checks that f of x is equal y. And now they both agree on the XOR of R and the pairwise independent, the hash of x. So let's see why this protocol works. So our first case is f is a permutation. And remember that in this case, we want to protect against malicious verifiers. So we don't know what the malicious verifier is doing, but he will send some y star and h star to the prover. The prover now chooses a random R and send it to the verifier, and the verifier sends some x star. But note that this x star better be x star that passes this test, because otherwise the prover catches the verifier cheating. And then they agree on this value. But if f star passes this, if x star passes this test, and f is a permutation, then actually x star was determined by y star. So x star was actually determined by when the prover sent this bit r. So this tells you that this is uniform, and r is independent of h of x. So this is the first case. Okay. In the second case, what happens with f is epsilon far from a permutation, then we want to protect against the malicious prover. So the verifier does what it's supposed to do. The prover, we don't know what he's doing. He sends some R star, and the verifier now sends X. And they both agree on this value. The important thing to note is that if f is far from permutation, and this is also was based on the soundness property, so the probability that y has two pre-images is at least epsilon, because the image of f is small. And I'm on time. So given this, we say that x actually has some entropy given y. So when the prover sees y, it doesn't actually know what the value x is. And because of that, we can use the leftover hash lemma and say that h of x is uniform even given y on h. So if h of x is uniform, then this value is also uniform. So this concludes the bit sampling protocol, and combining it with the honest verifier protocol that we saw, then we get the full protocol for permutation. Again, a very efficient protocol. Good. So let me conclude with some open questions. So the first one, can we come up with additional interesting properties in zero knowledge that has zero knowledge proof of proximity? One interesting one is the Hamming weight that was considered by RVW in the setting of interactive proof of proximity. And other, can we do it some for general classes of languages, such as context-free language and Rindbrand's matching program, that also has general interactive proof of proximity. Second is, can we import general statistical zero knowledge result to our setting of zero knowledge proof of proximity, such as malicious to honest, where we saw one example of that now, or complete problems, very interesting question. And finally, just because we talked about it, we don't know if double palindrome has a zero knowledge proof of proximity. That proof is certainly not one of those. Is it impossible to have such a proof? And that's it. I'm done. Thank you.